Welcome to the lesson about sensors for smart textiles and in the first video about strain gauges. A strain gauge is defined as a device used to measure strain on a material or structure. This device is able to make the link between the elongation of sensors positioned on a structure and a measurable physical quantity. Often, the measurable physical quantity is an electrical quantity. Thus, during the design of the sensor, the calibration phase occurs to build the mathematical relationship between the elongation of sensors and measurable physical quantity. When using the sensors, the aim is to use a mathematical relationship to evaluate the elongation of physical quantity measurement. A first example of an elongation sensor is the piezoresistive sensors. In piezoresistive sensors, elongation causes variation of electrical resistance of sensors from two origins. The first one is linked to the geometrical changes of sensors and described by the equation, where the measured electrical resistance is linked to the length and section area of sensors. This geometrical change occurs in all cases. The second origin of electrical variation is due to structural changes of materials. Rho in equation. Amplitude of these structural changes depends on the materials. It's null for the metal and can be important for conductive polymer composites. In smart textile field, used materials to develop the piezoresistive sensors are conductive polymer composite (CPC), with carbon, metal, or intrinsic conductive polymer as filler, but more and more intrinsic conductive polymer-based sensors are developed. Here is some example of piezoresistive sensors. On the left, a sensor based on conductive polymer composite on garment for posture monitoring, for sports or medical use. On the right, these sensors is also based on conductive polymer composite, but for aeronautical application in order to acquire data to feed mechanical models. Other possibility to evaluate elongation is to use knit sensors. In these sensors, elongation causes variation of electrical resistance of sensors from two origins. The first one is the geometrical changes of knit sensors. The second one is the structural change of conductive materials, here the conductive yarns. Indeed, when knitted is stretched, conductive yarns are crushed. The last one is a qualitative change in contact resistance between the conductive yarns during stretching. In smart textile field, used materials to develop knitted sensors are yarns made of or covered by metals, conductive polymer composites, or intrinsic conductive polymers. Here is some example of knitted sensors. This first study is about the knitting of polyurethane yarn coated with intrinsic conductive polymers. This sensor is used to evaluate the bending of knee for medical application. The sensor is glued on a garment. The second study is about the fully fashioned integration of conductive yarns. Two types of yarns are used, a blend of stainless steel and a silver-coated yarns. Once again, application is evaluation of posture for medical use. The interest of the knit sensor is a good integration of two textiles, level 3 or 4. Last possibility to evaluate the elongation is to use optical fiber sensors. In optical fiber sensors, elongation causes variation of gap between bright gathering, inducing the change in reflection and output spectra as is visible on the picture. The main advantage of optical fiber is that it can be directly embedded in or on textile structure. Here is an example of textile structure for ground monitoring. Even if optical fibers are not very flexible, application of on body are possible. Here is a belt for respiratory monitoring during MRI. This belt does not contain metal part and is fully compatible with electromagnetic fields.